Hello, everyone, and welcome to our next session at the Future of Electrification Conference. My name is Ryan Blackwell, Marketing Specialist at DeltaQ Technologies. Before this session gets started, just a reminder that it will be recorded and available to watch on demand afterwards. If you have any questions during the live session, please add them to the Q&A, which you can find at the top right corner of your screen. We'll be getting back to these and answering your questions at the end of the session. With that, I would like to introduce our next speaker, Rainer Kruse, who is the head of R&D and engineering at Schabmüller. Rainer will be speaking today on trends in motor design and finding the right solution for your application. Welcome, Rainer, and take it away.
So good morning, good afternoon. I'm happy to have you here. I need to make a correction. We are not speaking about trends in motor design. That was yesterday. We are speaking about why and how to avoid rare earth magnet motor solutions. So I'm happy to have you here. Let's just start. So talking about rare earth magnet material, I would like to show you first what are these kind of materials? Where do you can find them in the periodic table of elements? So here you can find the rare earths. It's this section and this section. These are all rare earth rare earth materials. The most common and most known magnet materials is, of course, the neodymium, dysprosium, samarium, well known from the samarium cobalt magnet, and you will find the ferrum, so which is in use for the ferrite magnets in combination with strontium and barium. Those materials are not rare earths, just those and those. So going to having a look to the global production and reserve of that kind of material. Over the years, I have the figures here for up to 2008 only, but there might not be a big difference here. One can see that there is here on the bottom, you can find some production in metric tons, other, so rest of world. You can find US going down here, and you will find the growing content of rare earth magnet material produced in China. One can find that situation also in the table below, showing the years 2010 to 2020, with the production in China and the other countries, and the reserve of the magnet material, rare earth magnet material in kilotons. Again, this is 2020 figure, and the total production and total reserve as known in that year. So this might open a little bit the picture, showing that the production is pretty much concentrated in one area, that there are reserves available. The name as such, rare earth, doesn't mean really that the material is rare. It's spread out all over the world, but it's almost very difficult to mine it and to process it. If we look to the properties of materials, the magnet materials, and here I would like to focus a little bit on the rare earth, neodymium, ferroboron materials, comparing the remnants and the energy product, comparing the rare earths to the strontium ferrite. One can see that the ferrite materials appear to be much weaker compared to the rare earth magnet materials. You can find in the middle, you can find the samarium cobalt and the alnico magnets, which is not so much in use anymore. So let's focus a little bit on the rare earths, and let's focus a little bit on the rare earth and the strontium ferrite magnet material. Looking to the neodymium ferrum boron, so the rare earth materials advantages, clearly the high remanence induction, the high coercitivity, and the high energy density are leading to a compact design of the electric machine, to a high level of torque density, to good efficiency, best efficiency, one may say, and to good power factor values. Of course, there are different grades of magnets available regarding remanence induction, regarding temperature, maximum temperature load, and other things, but that's not so important here. If we look to the neodymium ferrum boron rare earth disadvantages, of course, we can see the price development of rare earth materials, which is fluctuating a lot. Actually, we do see prices were growing during the last month. There was a period before that where it was very stable. One is faced sometimes with the situation that the export quotas are reduced, and all that can lead to a situation where the production cost of permanent magnet motors using the rare earth magnets are increasing. And now, looking to kind of like of a case study we did by simulating, I would like to show you what can be done in order to modify the design of an electric machine to get the rare earth magnet out of the machine, and what will be the effects, and what are the measures to be taken to get the ferrite material in the machine. So we compare here a machine. It's an 8-pole machine. We just show a section of the machine, one pole, one may say. And we always try to keep some elements constant, like the speed, the torque. Of course, that's what we want to see. The power output related to the torque, the motor current, the efficiency, the power factor, and the current density. And we have a look also to the magnet weight used and to the shaft diameter, which I explained a little bit later why this might be an important thing to know. So if we just try an one-to-one replacement of the rare earth magnet material using a ferrite material of a certain type, just put instead of the rare earth magnet some ferrite material, same amount of ferrite material into the machine, into the robot. One can see that the torque is going down by like 50%. So does the mechanical power output. This at the same motor current. The efficiency of the machine is still good. Power factor was dropping. We are working at the same current density. The magnet weight is a little bit less because of the more lightweight ferrite material. Density, lower density of the ferrite material. Shaft diameter is still the same. So just replacing against ferrite with no change in geometry of the magnetic circuit, the torque and the power will go down to like 50% of the original value. So if we try to compensate this by modifying the design to kind of like of a spoke design, where the magnet material, ferrite magnet material, is located in the rotor in a totally different arrangement, plus reducing the shaft diameter, we do see that we are now at 68% of the original value regarding the torque. Again, at the same current, at the same current density in the windings, but at larger magnet weight, of course. And we had to reduce the shaft diameter. So a little bit of improvement compared to the situation before. Next slide is showing a totally different arrangement, trying to place as much as possible of magnet material into the rotor. Now it is done in a fully different way. It's a V shape. It has multiple layers of magnet material embedded into the rotor. One can see, whoops, now we are already at 91% of the original torque. We are higher in power, of course. Again, we have to apply more current. In order to be able to do that, we had additionally to increase the slot surface to apply more copper into the slots by keeping the current density constant, of course, operating at higher current. The efficiency is fine. The power factor is not as good as it was in the beginning. And we had been able to apply a lot of magnet material, ferrite. But in order to do that, we had to reduce the shaft diameter as well. So now we are missing still like 10%. And here in the next step, again, further increase of slot. We are now back to like 98% of the original torque. Doing this with higher current, efficiency is still fine. So this is just showing that it is possible to supersede the magnet material, the rare earth magnet material against the ferrite material, but it's not so easy. You have to think a lot about your rotor design. You need to try to place as much as possible ferrite into your rotor. You have to increase the slot area to take more copper into the stator to keep your current density down in order to work with a higher current. So you pay a little bit with motor current, you pay a little bit with maybe cost of power electronics, but at the end it was possible to get very close to the original torque. Of course, this is a theoretical study, and not all designs will allow to find a way to place enough ferrite material into the rotor. Not all designs will allow to reduce the shaft size, and maybe also one will be limited with the increase of slot area to place more copper into the motor. Not to forget the situation with the power factor of the motor. This is not really bad, but one needs to keep an eye on that regarding the required inverter current or inverter current limitation, which may be there. And going to a larger inverter with a higher current limit, this for sure will cost some money as well. But this is just one way, showing one way to fully get rid of the rare earth magnet material and to supersede it with ferrite. So those are the measures to be applied. and a way to think about when trying to supersede this rare earth magnet materials. So I would like to show a little bit about the cost comparison, looking to the original version versus the ferrite version. This was the last one with the high quality ferrite magnet applied. So we have a magnet weight here of 1.9 kilogram roughly. In the ferrite machine, we have 3.3 kilograms. The magnet cost here is about, and this may vary grade by grade, this may vary with the temperature, this may vary on a daily base with the actual magnet cost. But let's say it's about 70 euro per kilogram for the rare earth material. Whereas for the ferrite material, you see something like 7 euro per kilogram. So the cost impact for this model we were looking at in this case study is about 118 euro, just the pure cost for the magnet material, compared to 23 euro for the ferrite material. So that's a rough cost comparison between those two variants. Of course, one can see a little bit that this machine has more copper. Copper also has its cost, but at the end, it will pay off. One can also always think about using no magnets. For example, going back to the good old induction motor, which has aluminum conductors, die-cast aluminum conductors in the rotor. And if we try to bring that machine in the same size to the same power output of about 100 kilowatt, we do see that we have to run it at a very high motor current, at a very high current density. The efficiency, naturally, the efficiency of that kind of machine is not that high like we have seen on the permanent magnet machine design. So what we see, low efficiency, power factor is low, running the motor at these conditions. There's a high level of rotor losses compared to the permanent magnet. Doesn't matter whether it's ferrite or rare earth, comparing to the induction machine, we do see a significant level of rotor losses. We have a high current density at the stator, comparing to the original value we were looking at. It was around 12. And that will lead to a situation that this machine cannot be operated continuously due to type S1. It can be operated, but not continuously. It may work in some applications, but comparing to the machine we had been looking to before, the main difference is, energy consumption because of the efficiency drop. And of course, it cannot operate continuously. So what might be the conclusion? In any case, design changes are necessary with the replacement of the rare earth magnets. Because of the efficiency and power factor drop, higher currents are required to reach the same performance. It's mainly related to the power factor. The higher currents lead to the different stator geometry to keep the current density constant in the motor. But it's possible. The motor shaft diameter in some cases must be reduced to provide the space for the larger magnets. A similar performance can be achieved with ferrite magnets in comparison to the rare earth magnets, in case these geometrical modifications can be applied to the machine. And there's another element. Putting a lot of magnet material in your rotor core will lead to a more fragile rotor lamination design and a higher magnet rate, and this may result in a lower speed limit for your ferrite machine. Just it may happen that the maximum speed you can reach with your motor has to go down because of the centrifugal forces and the mechanical structure uh, of the new rotor. For the induction motor, the terminal issues uh, look to be the no-go factor for superseding um, against the rare earth magnet PM machine. So how can this look like in practice? Those pictures are showing a rotor core segment from a machine equipped with rare earth magnets. It's an 8-pole design. The configuration is a V-shaped magnet, 2 magnets per pole. And looking to an permanent magnet motor type using ferrite material. This is showing the lamination. One can see how fragile it can be. And it's obvious how big the amount of ferrite blocks, the big of the amount of ferrite material is in comparison to the tiny magnets in the rare earth magnet machine. Really big blocks of ferrite introduced in a special configuration, which we call spoke design. Another way to use ferrite or to avoid, let's say, the rare earth magnet is to use the synchronous reluctance technology, which can work without magnet or with some layers of ferrite magnets. Also, this leads to a very fragile mechanical design of the rotor, and one may see these thin webs next to the magnets, which are necessary for the mechanical stability. One can see the thin webs next to these openings here, which are also necessary for this kind of machine design to make it work properly. But this is limiting the mechanical stability. So there's always the trade-off between what the electric engineer wants to establish in his electromagnetic circuit and what the mechanical engineer can allow regarding stability and top speed capability of such kind of rotor design. So that was about how to exchange how to exchange rare earth magnet material against ferrite magnets, non-rare earth material. But another step could be to think a little bit about how to reduce the amount of rare earth magnet material. If you cannot avoid it, you can try to reduce it. And for that purpose, I would like to show and share a comparison of 2 liquid permanent magnet machines. They are both equipped with rare earth magnets. They have the same magnetic circuit. They have finally the same mechanical output power in kilowatt. They use the same stator core diameter, same magnet quality, but they are much different in speed and torque level. So on the left-hand side, we do see a low speed, what I call low speed, high torque machine. At the right-hand side, we see a medium speed, low torque machine. It's not high speed, it's medium speed, low torque machine. Both machines have nearly the same output power, mechanical output power of 59 kilowatt, 58 kilowatt. The one machine reaches that output power at 1,700 RPM with 330 Newton meter. And for achieving that power output, we need a machine with a core length of 300 millimeters in order to get the torque out of that size. The machine has 160 magnets in total, and the magnet weight is 3.8 kilogram. So if we convert that machine to a medium speed, low torque machine, we can also get 58 kilowatt output power, but at 110 meter only, uh, 5,000 RPM. So the machine has the same core, but we only need a core length of 120 millimeter. So we have only 64 magnets in the machine. The total weight is 1.5 kilogram. So this is already a 60% reduction of magnet weight in this machine. So the difference is just here we create the power with a lot of torque, and here we create the power with a lot of speed. And this makes those machines so different. So I have one slide left. If we look into the efficiency plot of those two machines, there is another advantage, especially in this case. We can see that an S1 operating point, continuous toward operating point at the low speed and high torque machine is in the range of between like 92 and 94% efficiency, which is okay efficiency. But at the medium speed, lower torque machine, the same operating point, that's the 58 kilowatt, 59 kilowatt power output, is above 94%. So together with that medium speed, lower torque machine comes also a better efficiency, lower energy consumption, operating the same output power. So I think that was it. I'm at the end of my presentation. Um, and Ryan, if there are any questions, feel free to ask.
Right, for sure. Thanks, Reiner. So yeah, for those with any questions, make sure to type them in the top right corner in the Q&A section. It looks like we already have a couple. A bit tight on time, but we'll make sure to answer some of them. Here's the first one. What about induction machines with wound routers? Is this a valid alternative? We have seen recently the solution on a BMW application.
So wound rotor, and that was then not an induction machine, but that was a separate excited permanent magnet machine, I guess. Yes, this can be an option. So you supersede your permanent magnet field in the rotor against an electric excited field in the rotor. Um, Typically, there is you need a way to transmit your energy to the rotating part. In the past, this has been done with slip rings. So you have carbon brushes on slip rings, transferring your energy to the rotor. That's the old style. There are investigations. Some people do undergo investigations to have a wheel-less energy transfer to the rover. That might be an advantage for sure, and an option. You are on mute, Ryan, I think.
Thanks. Maybe we have time to slip in one more question. Would it be necessary to add a gearbox to the medium speed, low torque machine in order to supersede the low speed, high torque machine's performance?
Yes, of course, this is a valid question. Um, if you need if you have an application which requires that low speed output, in order to make use of that higher speed output, you need to add a gearbox between your application and the electric machine. And of course, this gearbox will also have an efficiency. That's why I was pointing to the fact that this machine has the better efficiency. Of course, uh, the adding a gearbox will lower your overall efficiency again, and also the gearbox has a cost, sure. But this is a good way to reduce magnet material, at least.
Hmm, right. Okay, well, it looks like that's all the time we have for today. There's a couple more questions coming in, but we'll make sure to answer those offline. Thanks so much for your time, Reiner, and to everyone who was able to join us for this session.
Thank you very much. Have a nice day.
You too.